Hello, this is ISAT430 Materials and Manufacturing Processes, Lecture 4, Polymers and Composites. All right, first we'll talk about polymers. In polymers, there are several topics. We'll first discuss a little bit about fundamentals, how polymers are formed, and what different categories of polymers. And then we'll discuss each of the categories of polymers. And then lastly, we're going to discuss a little bit about polymer recycling and also biodegradability. First, what is polymer? So polymer is actually composed of two words. One is poly and the other is mer. So poly means many and mer means part. So which means many different parts or many same parts. The polymers are usually based on carbon, and there are also some biological polymers. For example, cellular starch and something else, and as well as some new polymers. Usually those new polymers are synthetic ones, and the base material would be petroleum. So they are all made of petroleum because the base element is actually carbon. Something we need to note is that general categories of polymers are thermoplastics, thermosettings, and also elastomers. And the thermoplastics is usually composed of about 70% of all polymers we see in our lives. And we'll discuss each of the category in the next few slides. In general, the reason we want to use polymers is because it's compared to metal and ceramics, it's actually a little bit lighter, right? So because they are low density, and also they have a high corrosion resistance. Metals sometimes they easily cannot prevent from corrosion because oxidation of the surface. And also polymers, because of they have very stable structures, so they have low electrical and thermal conductivity. Compared to metals and ceramics, also polymers are cheaper, and also require less energy to produce than metals because of the embedded energy. In order to cut metals or process metals, usually requires more force and more energy or more power to process metals compared to polymers. And also some of the polymers, they are transparent, so there are many applications of that. For example, helmets, right? And also some of the places that need transparent walls or transparent parts. There are also some limitations of polymers because polymers are very vulnerable to high temperature. So when the temperature is high, usually it will reduce its not only mechanical property but also some chemical properties as well. And also compared to metals and ceramics, polymers usually have the strength is a little bit low, and also Young's modulus is also low. So how the polymers formed, and usually the polymers actually form with a chain. So this chain, you can see this part is actually one base component, and because there are many mers, for each mer is called a monomer, and then when they start to form a chain-like structure, you will see they will look like more like this. Okay. And n here, you can see this n is actually an average number because in a polymer or in a plastic material, and usually there are chains like maybe 2, maybe 3, or maybe many large numbers, and this form a distribution. This forms actually statistical distribution, and this n is the average number for those. So this is how we write this polymers. And because of those forces are actually van der Waals forces, so you can see that's why polymers usually have, their structure is actually weaker than metals and ceramics. A couple different ways for polymerization. One is addition polymerization, and also the other one is a step polymerization. First, let's look at addition polymerization. So, addition polymerization means first, because there's a carbon-carbon double bond between carbon atoms. So, in order to create a new structure or add a new structure on it, first the carbon bond need to be opened, and then to form another carbon structure on it. So this is how you add another structure on it. So this is called addition polymerization. You need to open up this double bonds between the carbon atoms, and there are many structures or many materials are this kind of a way to make for polymerization. For example, polyethylene and PVC and something and polystyrene, all of those materials. And a common thing about or common form of this kind of material is that you can see this is usually they have one single structure inside, right? One single structure inside, and then you have an N, like how many those kind of simple structures or single structures are formed of this kind of material. So and those are common. Usually they are thermoplastics. Well, compared to addition polymerization, now let's look at step polymerization. So step polymerization means there are two acting monomers, right? Two acting monomers are brought together to form a new molecule of the desired compound. It does not have to be the the carbon and carbon bound. Instead, they can be some other. For example, there's a carbon, there's a chloride, right? So maybe this chloride is connected to something, and then it start to form another structure. So in this case, there are some reacting monomers, and they form a new structure. So this is how step polymerization happens. Well, how to calculate and what is the length of those? Usually, if it is one, say N1 mers and N2 mers, when they merge or when they start to react, actually will form N1 plus N2 mers. So this is called step polymerization. And there are some examples of step polymerization materials. You can see these are other structures formed, and then this kind of bigger unit or bigger single structure will be repeated with n times, right? N is the average number. So and material will be like polycarbonate, and also nylon and some other materials. Something to remember is that during the step polymerization, because there are some reactions, there will be also some byproduct generated from the reaction. For example, these can be the byproduct generated from some materials. So for degree of polymerization and Usually, a given batch of polymerized material it varies in length. As we discussed before, it can be and can even in the same material it can vary from a very large number, maybe 1, 2, maybe 3, maybe 1,000, maybe more. And so that's why n for this kind of batch is actually a average number of those because it follows a statistical distribution. Okay. And so how to calculate the molecular weight? Basically, it's a sum of the molecular weights of the moles in a molecule at n times the molecular weight of each repeating unit. Right. We have a polymer, and there are some structures, and then we have the n. Then we can use the n to times the weight of this repeating unit. This is the repeating unit. Now let's look at different structures of the polymers. And the one structure of the polymer is the linear structure. So linear structure basically is one single line or one single chain. You can see there are no branches. Well, the branched structure means you can see there are some branches formed from the main chain line, right? This is a one chain, but there are some branches formed. Well, another type of the structure will be the cross-linked structure. So which means there are multiple chains, right, and also some cross links between the chains, right? Cross links between the chains. Because they form this cross link of the chains, usually those kind of material actually have higher strength, right, stiffness and toughness compared to linear structures. So thermoplastics polymers, commonly we can see PET, HDP, LDP, those kind of polymers always possess linear and or branched structures, or sometimes it's a mixture of the two. And when the branches increases, it actually will make the polymer stronger in its solid state. And it also will be more viscous, at higher temperature when it's converted to liquid state. Well, for crosslinks, thermosets usually have a high degree of cross-linking, and elastomers also has cross-linking, but it has a low degree of cross-linking. It's not as high as thermosets. So elastomers, for example, the rubber, right? Usually thermosets are hard and brittle, and elastomers are elastic and resilient. So that's because crosslinks cause the polymer to become chemically set. And means the reaction cannot be reversed. So if you heat a thermoplastic, usually you can it will convert it to a liquid state, and when you cool it down, you can actually convert it back by by injection molding or some other ways. But for materials or polymers have crosslinks, it's a bit hard because it's very hard to go back to its original cross-linked structure. That's why some of the material will be either burnt, right? Either burns or it just degrades, and the structure is permanently changed. This is also the difference between thermoplastics and thermosets and elastomers. So crystallinity. So both the amorphous and crystal structures are possible in polymers because they're not metals. So their crystalline structure is less likely, or amount of the crystalline structure is less than the metals or ceramics. And not all the polymers can form crystals, and a lot of times even they form some of the crystals is only part of the structure, right? So part of the structure is actually has this crystal structure. So when the polymers have some crystallinity, what it means is that its density will increase. So basically, it will start to perform some or have some properties like metals, right? Stiffness, strength, and toughness, and also heat resistance. And if the original polymer is transparent, in its amorphous state, if they have some crystalline structures, which means that it will become opaque, because it forms actually a more solid and crystalline structure in that polymer. You can see a difference of the two different types of polyethylene. So one is low density one, while the other one is high density one. So this is LDPE, usually we call it, and this is the HDPE material. Usually you can see LDPE and HDPE in a lot of containers or in a lot of plastic products. So you can see that LDPE compared to HDPE crystallinity for HDPE is 92%. So that's why HDPE is stronger and higher stiffness than LDPE. Same with gravity, right? It's heavier than that. Melting temperature is also higher than LDPE because of the higher degree of crystallinity. Different factors will affect crystallization. So one is cooling time. So if you slower cooling the material, it actually promotes crystal formation and growth. Think of the glass. When we're making glass, so this is basically slow cooling to make that, and also as it stretches, of a heated thermoplastic, it tends to align the structure and increase crystallization. So, right, mechanical deformation can also increases this crystallization. Also, sometimes you add some plastic sizers and to reduce crystallinity. Now let's look at different structures of the polymers and how they affect its thermal expansion property. So because crystalline structure will our polymers with some of the crystalline structure will perform some of the properties like metals. So that's why crystalline polymer, you can see if it is high degree of crystalline structure, then it will actually start to perform this kind of behavior, like a sudden change of the volume, right? So the melting temperature compared to a partially crystalline polymer, while compared to amorphous polymer, it's more like glass or typical amorphous structures. So this is how this crystallization actually affect the polymer's properties. And when we are making different kind of polymers, and also we can use additives to modify the property of the polymer materials. So the function is to alter the molecule structure or add a second phase, right, in the structure to transform the polymer into a composite materials. And there are different functions or different purposes of additives. Some of the additives are to increase the strengthness of the materials. Some of the polymers, some of the additives are for colorization. Some of them is to to increase the plasticizers, right? Increase the polymer forming, and also some of the additives can for lubrication, so that you can reduce the frictions and improve the flow. For example, you can use this for some of the polymers that are making bearings, right? Because when you are using some of the bearings, we want to reduce the friction, so there's less energy waste. Also, you can add additives to reduce the the flame, to have the flame retardants. Cross-linking agents, so some of the materials, some of the additives can helps forming cross-links, right? And some of the additives also reduce degradation from sunlight, so they can absorb UV light, okay? And some of the additives are antioxidants, so they can reduce the oxidation damage. Well, for the three types of the polymers, the first big type is thermoplastic. So thermoplastic can be heated from solid state to viscous liquid state and then cooled back down to solid. This kind of heating and cooling, it can be repeated many times without degrading the polymers. So because the reason that they can be repeated without degradation is because thermoplastic polymers, they consist of a linear or some of the branched molecules. They do not have this cross links, so the structure is not that complicated, and they can easily to form back to its original chain or branched molecule chain. Well, the thermostats and elastomers, it can change chemical. They change chemically when heated. So the crosslinks actually are broken, right? So it's hard to form back to its original crosslinks. So that's why the chemical structure properties actually already changed. So the typical thermoplastic polymers, the mechanical properties are they have a low Young's modulus, so which means their stiffness is a little bit low. Same with the tensile strength and also hardness, but they have a better ductility on average compared to metals and also the other materials. And those thermoplastics usually have lower densities than metal and ceramics, but have a much higher coefficient of thermal expansion. We saw that from the graph, right? And usually that's about 5 times the value for metals and 10 times the value for ceramics for thermal expansion. Also, for polymers, especially thermoplastics, they can only work or operate in low temperature conditions. So because their melting temperature is low, if you increase temperature, you make damage its mechanical property, and then will affect its function. but thermoplastics, they have insulation property, so they do not conduct electricity. So this is a comparison of typical thermoplastic polymers. It's a table. You can see there are many different types of thermoplastics, and this is a comparison. You can find some typical ones. For example, polycarbonate, polyester, and polystyrene, PVC. So they usually have really good Young's modulus, right? They usually have really good Young's modulus, while some others might have not. And if you look at specific gravity, you can find what polymers, what thermoplastics are usually higher or heavier than others. For example, acetal is typically heavier than polyethylene, low density polyethylene, LDPE, right? So you can use this table as a guide for for these mechanical properties when you are choosing materials. Now let's look at different types of thermoplastic polymers. One typical one is acetal. So usually these kind of polymers are with high stiffness, strength, and also toughness, and also have wear resistance. So that's why they can be used in products that need to be operated in some conditions that require good strength and toughness and wear resistance, like bearings, right? Bearing or door handles, pump housings, and also some appliance hardware and also machinery components. So something to keep in mind is that even though that the polymers are different, they might have the same appearance. So for example, this maybe let's say this is door handle, okay? Even though this is made of acetal, maybe sometimes can also be made of PVC. It may have the same appearance, but the mechanical properties will be different. Right? Will be different. Another type is acrylics. We are pretty familiar with acrylics. Because there are many products are made of this material, made of this polymer. One typical one is a tail light lenses, right? Tail light lenses of the cars, and this is the main material of acrylics because they are transparent. So this is one typical character for acrylics, and also some other, for example, this window, right? The aircraft windows, some optical instruments, floor wax, or latex pens. All these applications can be, this can be applications for acrylics. Another transparent material is a polycarbonate. While both are transparent, actually polycarbonate have higher strength than acrylics. And also it has really good heat resistance. It can be used to temperatures around 125 degrees. All right. So typical applications for polycarbonates will be actually similar to acrylics, but you will have to consider if that part or products really need high strength for operation. for example, helmets, right? Helmets, glazing applications, housings for business machines, and also molded parts. It's not always that the polycarbonate has to be transparent. So some of the polycarbonate, it actually has some colors, right? Have some solid colors. So it can just make sure you know that it's not always transparent. It really depends on how you process the polymer. When we're cooling down this, and the transformation process will affect its transparency. Well, another type of material is thermoplastic is ABS. ABS is another common polymer we see in appliances or in especially in plumbing, right? There are pipes, fittings. Usually you can see this ABS material is very hard, right? It has a very good mechanical property, and also is relatively chemical stable. Another type is cellulosics. So cellulosics, it has been used a lot in clothes industry, and also for films, right? Photos, so it has been used a lot. So this is cellulosics. Fluoropolymers. So for this type of polymers, usually, commonly it's actually telephone. We hear this word probably from the from our cooking ware, right? So when you go to the store, you might see this telephone material for pans or for cooking. And because they have a really good heat resistance and also low efficient of friction, and affected by water, and also chemical stable, and so because of those properties, they can be used in some of the high temperature environments like cooking, or in some processor that is for processing food, right? Processing food. So polyamides, a common type of this polymer is nylons. So nylon has been used a lot in carpet, apparels, and tire cords. Some tire cords is also made of nylon materials, and same as bearings, gears, and also some engineering parts that requires high strength and also low friction, right? So this is polyamides. And polyesters, and this is very common in our life. So very common is the PET material, because we usually see the bottles, right, with PET label on it. So this is the PET materials. One character or one property of the PET material is they can be very highly transparent. So, for example, this kind of film, these kind of bottles, containers, can all be made transparent. So polyethylene. So polyethylene is another big type of thermoplastic that widely used in our lives. And polyethylene usually can be low density polyethylene and also high density polyethylene. And so for low density polyethylene, probably you usually see that in plastic bags, right? In plastic bags, usually that is low density polyethylene. While in high density polyethylene because they have a denser, stiffer, stronger, and high melting temperature, so they can be made into some containers that like this, right? Require higher strength, and also pipes and housewares, bottles, right? For high density polyethylenes. Well, polypropylene is also a large type of thermoplastic, right? So we usually call it the PP, polypropylene, and it has really good strength to weight ratio. So which means that if you are looking for some material or some polymer with lower weight, but it has really good strength, then maybe this is a good option for the part. And polypropylene has been widely used in injection molding, in some fiber products, carpets, and also one-piece hinges. Well, polystyrene, usually commonly we see the foam, right? They have been used in packaging, in some kind of food containers, or as this kind of foam, because they are very brittle, a little bit transparent, and it also can be easily colored, right? Readily molded using injection molding, but it has really good toughness for polystyrenes. PVC. So PVC. When you hear about PVC, you probably see, it's very strong. It has used a lot in the pipes, right? In plumbings, in fittings. So that's why PVC with its very very high strength, and also good strength property. It's been used a lot in plumbing materials, but it can also be made into very flexible materials. For example, some bags like this, right? Packaging, and also sometimes the films as well. So PVC is actually a very good material for making pipes and fittings. Something I forgot to mention is it's not very stable to heat and light. It's not very it's a little bit vulnerable to UV light. So usually when you are making those PVCs, they actually you can either have some of the coatings on it, or you can make some of the composite materials in order to based on the PVC in order to increase its other kind of properties. All right, so that's all these types are materials or polymers are thermoplastics, right? Now let's look at thermosetting polymers. Thermosetting polymers, we mentioned that they have cross-linked, right, three-dimensional covalent bonding structure, and they cannot, after heated, they cannot go back to its original state. So these are the thermosetting polymers. The common type thermosetting polymers are resins, right? So general properties of thermosetting polymers, usually they are rigid, brittle, virtually no ductility, and less soluble in common solvents than thermoplastics. So they cannot be remelted. Instead, they degrade or just burn. But they can operate in relatively higher surface temperatures than thermoplastics. Some typical products, thermosetting products are countertops, plywood adhesives, pins, molded parts, or some printed circuit boards, and then some other fiber reinforced plastics are all thermosetting polymers, right? A very common one is phenolic resins, right? Last one is elastomers. So elastomer, basically they are usually call it the rubbers, and they have really good elastic property. That's why they can be used a lot in the tire industry. And for making the rubbers, there are two types of rubbers. One is natural rubber, another one synthetic polymers. So the reason that rubbers or elastomers can tolerate really high stretch, and then they can again return back to its structure is because when they have they have really high degree of cross linking, right? These cross links can be stretched and then return back to its original structure. Well, another high degree of cross-linking polymer is thermosets. So thermosets actually have more cross-linking than elastomers. For typical rubbers, usually in hot weather they can become a little bit sticky, while in the cold weather they can be stiff and brittle. And usually when we are making rubber, so something we call it vulcanization. So which means we use sulfur. Right, so we include sulfur material into the rubber so that it can increase its cross-linking. So you can see the comparison between the three different rubbers. So one is crude natural rubber, vulcanized rubber, and also hard rubber, right? So this is the stress strain comparison. Natural rubber. So natural rubber usually derived from latex, so which is a milky substance, produced by various plants. And it's very important because you usually can get from rubber tree, and those kind of trees usually grows in tropical climates. And for the vulcanized natural rubber, usually they have the properties of high tensile strength, tear strength, and also resilience and resistance to wear and fatigue. So the weakness for those rubbers is that they degrade easily when it is exposed to the heat, sunlight, oxygen, ozone, and oil. But when also increase or these kind of properties by adding some additives, we mentioned before. So natural rubber products are usually used a lot in car tires, right? Some other products will be bushings, shoes, seals, and also some shock absorbing components. And when we are making tires, a lot of time we add a carbon black, so it reinforces the rubber, serving to increase its tensile strength and also resistance to tear and abrasion. So synthetic rubber. Those kind of synthetic rubber was developed because during by the world wars, when natural rubber was difficult to obtain, so that's why we can use synthetic rubbers, and a lot of those actually there are more than 3 times than that of natural rubber, the production. Last, discuss a little bit about polymer recycling and biodegradability. So we know that plastic has been widely used in our lives, and every day actually a lot of plastics waste generated. But those for those plastic waste, most of them are actually either incinerated or landfilled, so they are not recycled because biodegradable plastics is a very small percentage of all the plastic we use in our lives. So the reason that why plastics recycling is difficult is because plastic products are generally small and made of a great variety of chemical components, and we cannot mix them. It's not very good to mix them and then to make a brand new product with the same property. So that's why recycling has been really difficult. Especially if you want to recycle them, then you have to really, at the very early stage of recycling, you have to sort them well into different categories of the polymers that we mentioned before. There are a lot of types of polymers, so which means that you need to know very well about those products and what type of material they use, and then to send it into different processing paths. So that's why it has been high cost of recycling plastics. But there are some of the efforts existing right now. For example, some plastics have been used to make construction materials, bricks or foundations, and also as fittings for some other structures. So they can also it has been used in those kind of ways. There are also some of the efforts that trying to make plastic or make different polymers into very valuable products. For example, you can reprocess those thermoplastics into valuable products like arts, artifacts, or 3D printing filaments, for example, and also some other useful products that can generate value. And for polymers, now there's a plastic identification code. So commonly we see that from 1 to 7. I think it will be good for you to remember those. And it actually is not hard to remember because it starts from 1 as a PET, because PET, think about our bottles, right? Containers, water containers, and it's probably the most common polymer we see in our lives is PET. Then next is low density polyethylene. So, for example, our plastic bags, right? In supermarkets. Another one is polyvinyl chloride, which is PVC, that we mentioned before, those kind of pipes, fittings, really hard, parts, polymer parts or plastics. So we use PVC, and then the next one is LDPE. So LDPE, those kind of low density polyethylenes. Polypropylene. We mentioned that it has been widely used in injection molding, right? Injection molding, and polystyrene, that's the foam, and also the last category is it's all the other polymers will be in the code 7. For example, ABS, and also polycarbonate. So this is why recycling of the plastics has been difficult. And for biodegradable polymers, so usually they can decompose due to actions of microorganisms in nature. But those degradation can degrading process can take about sometimes several months, maybe not in days, but usually it takes several months to degrade. Those are some of the applications of biodegradable polymers. It'll be good to watch this video, so I think to enhance your learning about the polymers. Let's look at composites. So composites usually they are the materials that are composed of two or sometimes more distinct phases of materials, and those materials they usually have different properties, and putting them together because we want to have the both want to have create a certain material system that can have both advantage of those properties. And some of the examples would be ceramic carbides, plastic molding components with some fillers, and also rubber mixed with carbon black. For example, when we are making tires, it's actually it's composite materials, but it's a little bit more complex than just rubber with carbon black. It also has our other structures, and so the reason people are using composite material is because that sometimes we want those kind of polymers or plastics or metals or ceramics perform in some extreme or higher demand environments. For example, higher strength, higher stiffness, right? And also we want to have lightweight structure, right? The strength to weight ratio or the stiffness to weight ratio to be high, so that we and also sometimes we probably don't want to use all metals. Maybe you can mix some metal with some plastics, right? So that then create something that can be both high strength and a little bit light, right? So this is why that composite materials are created by combining the strengths of all the constituents. Also, there are some disadvantages or limitations. For example, if you are using polymer-based composites, or the material the composite material, it has some polymer elements, usually they they are sensitive to either high temperature or some chemicals or solvents. So this is some of the limitations. So application of those material will be limited. And also, composite material are generally expensive because of the manufacturing process. It's much more difficult than pure or simple material structures. And so most of the composite material consists of two phases, and one is the primary phase, the other one is the secondary phase. So primary phase, it forms a matrix, right? The secondary phase, it's something that added on it, right? As more as a reinforcing agent. So based on its matrix, there are metal matrix composites, ceramic matrix composite, and also polymer matrix composite. We can see some examples in this table. So this is the primary phase, and this is the secondary phase. So you can see if metal is a primary phase, or it's a metal matrix composite, right? Metal can be mixed with metal, with ceramics, with polymers, and also other elements like boron and carbon, right? This is boron, this is carbon, and they can create products, different products. For example, in metal, then we see a lot when we are talking about metals, right? So composite metal materials like powder metal parts, infiltrated with a second metal, and also when metal is a matrix and ceramic as the second phase, then we can make product like cermets, right? And also fiber reinforced metals. Metal can also be mixed with polymers. So some of the powder metal parts impregnated with polymers, and also some fiber reinforced metals when it is mixed with boron or carbon. For polymer, if the polymer as a primary phase, or it's polymer matrix, same, it can be mixed with all the three materials: metals, ceramics, polymers, as well as boron and carbon. But if it is ceramics, so because ceramics is very, very stable structure and is very well condensed, so it's a little bit hard to be mixed with other materials, for example, metals, polymers, and boron and carbon. But ceramics can only be mixed with ceramic materials, right? So this is the matrix. So what kind of elements or what kind of material can be used as a matrix, primary phase, and what material can be used as a secondary phase, and what products are made here. In terms of the reinforcing phase, there can be different shapes. Typical shape is kind of fiber shape, and also sometimes it's particles, and sometimes it's flakes. So these are the three most common shapes. And for the fiber ones, usually those these are the filaments are reinforcing material, usually circular in cross sections, and diameters it varies from 0.001 inch to 0.005 inch, so it's very tiny, small. And so having those kind of fibers or filaments, it can actually increase the strength of the composite. In terms of the orientation, it can be one orientation, like one dimension, or it can be a planar dimension, or it can be random, right, discontinued fibers. So there are different types of shapes of the fiber. And for fiber materials, it can be all the material that we talked about before. It can be glass, can be carbon, boron, or polymers, ceramics, and metals. It is the metals. A lot of times we see it's a steel, as a fiber. The ceramics, like silicon carbide, right? Alumina, and if it is a carbon, it can be it can increase its elasticity, right? Modulus. Another two forms or shapes are particles and the flake. So just to make sure you know these kind of two shapes are also used. So for bonding, between the different phases of composite materials, so one type bonding is the direct bonding. So direct bonding is more like this. You can see it's it does not have this kind of transition area. Well, there's another one is interface, right? Interface bonding. So this is the secondary phase. This is the primary phase. Well, in between there's the interface. It's a certain ingredient can be used in order to form the bond between the two materials. So the third one will be more like adhesive materials. All right. Lastly, there are some composite structures. So composite structures, it can be conventional structures, for example, like different layers added up all together. We create a composite structure, or it can be a sandwich structure, right? We have the top layer, lower, bottom layer, and in the middle we'll have another structured material, right? So for example, foam material, or something else. So this is a sandwich structure, and also you can be creative to create some unique structures. For example, honeycomb structures, right? Honeycomb structure, or some other structures in between, and these kind of composite materials. Actually, they have been used a lot in lightweight material design, and for example, in aerospace industry, people have been used a lot in this kind of composite materials in aircraft structure, or some of the plates that require higher strength and also go to a strength to weight ratio. All right, so that's about composite materials and also the polymers, and these are some of the typical questions for the quiz and also takeaways. Just make sure you go back to to the lecture slides and also watch the video and finish the quiz and homework assignments. All right, that's all for this lecture.